The Tacoma Narrows Bridge, 1940.
In 1940, the Tacoma Narrows Bridge opened in Washington state. It was the third longest suspension bridge in the world, elegant, modern, and innovative. Engineers had designed it to be lighter and more flexible than previous bridges, using a new streamlined deck design. The bridge was beautiful. It was also fundamentally flawed. From the day it opened, the bridge moved. Winds would cause the deck to undulate in waves, earning it the nickname Galloping Gertie. Drivers reported feeling seasick crossing it. Some people drove to the bridge just to experience the thrill of the rolling deck. Engineers noticed the problem, but the bridge had just opened. Fixing it would be expensive and embarrassing. 4 months later, the bridge collapsed.
The design used a solid plate girder system instead of open trusses. This made the bridge lighter and cheaper, but it also made it more susceptible to wind forces. The narrow, flat deck acted like an airplane wing. Wind could create aerodynamic lift and torsion. Civil engineer Leon Moisseff, the designer, had used mathematical formulas that worked for static loads, but he didn't account for dynamic wind forces, the way wind could interact with the bridge's shape to create oscillations. When engineers noticed the dangerous movements after opening, they proposed solutions: wind baffles, cable stays, modifications to the deck. All were rejected as too expensive or too disruptive to traffic.
What went wrong? On November 7, 1940, sustained winds of 42 miles per hour hit the bridge. The deck began oscillating violently in twisting motions. The oscillations built on themselves, a phenomenon called aeroelastic flutter that wasn't well understood at the time. Within hours, the bridge was twisting so violently that the roadway was nearly vertical. Then, the main span tore apart and collapsed into Puget Sound.
The consequences. The Tacoma Narrows collapse fundamentally changed bridge engineering. Engineers realized that aerodynamic forces had to be considered in design, not just static loads. Wind tunnel testing became mandatory for major bridges. The concept of aeroelastic flutter entered engineering curricula worldwide. Modern suspension bridges look different, with open trusses and wider, more stable decks, specifically because of lessons learned from this failure. The bridge was rebuilt in 1950 with a completely different design. It's still standing today. The pattern begins, ignoring warning signs, the oscillations, to avoid cost and delay leads to catastrophic failure.
The Hyatt Regency Walkway collapse, 1981.
The Hyatt Regency in Kansas City was a stunning modern hotel featuring a multi-story atrium with suspended walkways connecting the buildings across the open space. 2 walkways, one on the 2nd floor and one on the 4th, hung from the ceiling by steel rods. The original design called for single continuous rods running from the ceiling through both walkways. The upper walkway would hang from the rods, and the lower walkway would hang from the same rods further down. During construction, the steel fabricator asked for a design change. Instead of long, continuous rods, use 2 sets of shorter rods. The upper walkway would hang from the ceiling, and the lower walkway would hang from the upper walkway. This seemed like a minor change. It wasn't.
The original design had each walkway supporting only its own weight. The modified design meant the upper walkway had to support both its own weight and the lower walkway's weight, essentially doubling the load on the critical connection points. The engineer approved the change with minimal review, apparently not recognizing how dramatically it altered the load distribution. The fabricator thought the engineer had done the calculations. The engineer thought the fabricator understood the implications. Nobody properly analyzed the modified design.
What went wrong? On July 17, 1981, the Hyatt Regency hosted a popular tea dance in the atrium. Approximately 1,600 people packed the lobby and walkways to watch and participate. At 7:05 p.m., the upper walkway's support rods pulled through the box beam connection. The fourth-floor walkway fell onto the second-floor walkway directly below it. Both walkways then crashed into the lobby floor. 114 people were killed. Over 200 were injured. It remains one of the deadliest structural failures in U.S. history.
The consequences. Investigations revealed the connection was severely underdesigned. Even the original design was inadequate, calculated to carry only 60% of the required load under building codes. The modified design cut the load capacity in half. The engineers had stamped drawings they hadn't properly reviewed. The contractors assumed engineering approval meant the design was safe. Communication failures and lack of oversight allowed a fatally flawed design to be built. Both the engineering firm and individual engineers lost their licenses. The disaster led to major reforms in engineering liability, drawing review processes, and the professional responsibilities of engineers. Kansas City updated building codes. Engineering ethics courses now teach the Hyatt Regency collapse as a case study in professional responsibility. The pattern continues. Design changes without proper analysis. Assumptions about who checked what. Cascading failures in oversight. Space Shuttle Challenger, 1986. The Space Shuttle was supposed to make spaceflight routine and affordable. By 1986, NASA had completed 24 successful missions. The program was under intense pressure to maintain an ambitious launch schedule and demonstrate reliability. The Challenger mission was special. It would carry Krista McAuliffe, a teacher, as part of the Teacher in Space program. Millions of school children would watch the launch live. Launch was scheduled for January 28, 1986. Overnight temperatures at Cape Canaveral dropped to 18 degrees Fahrenheit, far below the minimum temperature at which the shuttle was certified to fly. Engineers at Morton Thiokol, the company that built the solid rocket boosters, were alarmed. The solid rocket boosters were constructed in segments, sealed by O-rings, rubber seals designed to prevent hot gases from escaping during launch. Engineers knew the O-rings became less flexible in cold temperatures. Previous launches had shown O-ring erosion and blow-by, hot gases leaking past the seals. Engineers had documented this problem. They had warned management. They had explicitly stated that launching below 53 degrees Fahrenheit was dangerous. The night before launch, Thiokol engineers recommended postponing. They presented data showing O-ring problems correlated with cold temperatures. NASA management pressured them to reconsider. There was schedule pressure, political pressure, media attention. The teacher was waiting. They couldn't keep delaying launches. Thiokol management overruled their own engineers and recommended launching. What went wrong? At 11:38 a.m. on January 28, 1986, Challenger launched in 36 degrees Fahrenheit, the coldest launch in shuttle program history. 58 seconds into flight, hot gases began leaking through a primary O-ring that had failed to seal properly in the cold. The gases eroded the O-ring and burned through the external fuel tank attachment. At 73 seconds, the external fuel tank ruptured. The resulting fireball destroyed the orbiter. All 7 crew members died: Francis Scobie, Michael Smith, Ronald McNair, Ellison Onizuka,
Judith Resnick, Gregory Jarvis, and Krista McAuliffe. Millions of people, including countless school children, watched them die on live television.
The consequences. The Rogers Commission investigation found that NASA had known about the O-ring problem for years. Engineers had warned repeatedly. Risk assessments had been ignored or overruled because of schedule pressure. The Commission found NASA's organizational culture prioritized maintaining the launch schedule over safety. Management had normalized the O-ring problems, convincing themselves that because previous flights hadn't catastrophically failed, future flights would be fine. Physicist Richard Feynman, a commission member, demonstrated the O-ring failure mechanism in a famous televised hearing by immersing a sample O-ring in ice water and showing how it lost flexibility. NASA grounded the shuttle program for 32 months. Safety procedures were overhauled. The O-ring design was changed. But the fundamental lesson, that schedule pressure and bureaucratic momentum can override engineering judgment, remains relevant. The pattern. Known problems documented, warnings given. Management pressure overrides engineering judgment. Catastrophe results.
The Banqiao Dam collapse, 1975.
The 1950s, China embarked on massive dam construction projects to control flooding and generate hydroelectric power. The Banqiao Dam on the Ru River was designed to withstand a 1-in-1,000-year flood, meaning a flood so severe it would only occur once every 1,000 years on average. Chen Xing, a hydrologist, warned that the dam's design was inadequate. He advocated for more spillways and floodgates to handle extreme flooding. His warnings were ignored, and he was labeled a right-wing opportunist during the political climate of the era. The dam was completed in 1952. It was considered one of China's engineering triumphs.
The Banqiao Dam was part of a system of dams along the Huai River basin. Engineers designed it with specific assumptions about maximum rainfall and flood levels. Those assumptions were wrong. In August 1975, Typhoon Nina stalled over the region and dropped a year's worth of rain in 24 hours. The Banqiao Reservoir filled faster than the spillways could release water. Operators tried to open sluice gates to release pressure. Some gates were jammed with silt. Others had been designed too small. The dam wasn't built to handle this much water this quickly.
What went wrong? On August 8, 1975, the Banqiao Dam failed catastrophically. The entire dam structure collapsed, releasing 15.738 billion cubic meters of water in a single wave. The flood wave was over 10 kilometers wide and several meters high, traveling at 50 kilometers per hour. It destroyed everything in its path: villages, towns, farmland, infrastructure. Worse, the Banqiao Dam collapse triggered a domino effect. 62 downstream dams also failed, creating multiple waves of destruction across Henan province.
The consequences. The death toll is disputed because the Chinese government suppressed information for decades. Conservative estimates: 26,000 people drowned immediately. Another 145,000 died from famine and disease in the aftermath. Some estimates put total deaths as high as 230,000. 11 million people lost their homes. The disaster destroyed infrastructure, agricultural land, and economic productivity across a vast region. The Banqiao Dam failure is considered the deadliest structural failure in human history. Yet most people have never heard of it because the Chinese government classified it as a state secret for decades. Modern analysis shows the original critic, Chen Xing, was right. The dam needed more spillway capacity.
His warnings were ignored for political reasons. Acknowledging flaws in such a major project would have been embarrassing. The pattern: political pressure silences engineering dissent. Inadequate safety margins lead to catastrophic cascading failure.
Grenfell Tower Fire, 2017.
Grenfell Tower was a 24-story residential building in West London. Built in 1974, it underwent a major renovation in 2016 to improve its appearance and energy efficiency. The renovation added external cladding, aluminum composite panels with a polyethylene core to improve insulation and modernize the building's appearance. This was common practice in modern building retrofits. But the specific cladding material chosen was highly combustible, and it was installed with flammable insulation behind it, creating a gap that would act like a chimney in a fire. Residents had repeatedly raised safety concerns. They warned that there was only one stairwell for evacuation. They noted that fire safety equipment wasn't working. They complained to management. Those warnings were ignored or dismissed.
On June 14, 2017, a refrigerator in a fourth-floor apartment malfunctioned, starting a small kitchen fire. Under normal circumstances, this would have been contained to a single apartment. UK building codes are designed with compartmentalization in mind. But the fire spread to the external cladding. The aluminum composite panels had a polyethylene core, essentially plastic sandwiched between thin aluminum sheets. When heated, the plastic ignited. The cladding burned rapidly, spreading flames up the outside of the building. The gap between the cladding and the building acted as a chimney, accelerating the fire's spread. In minutes, flames engulfed the entire 24-story tower.
What went wrong? First, flammable cladding. The specific cladding material used was banned in many countries for high-rise buildings because it was known to be combustible. UK regulations were inadequate. Second, cost-cutting. A fire-resistant version of the cladding was available, but cost slightly more. The cheaper, combustible version was chosen to save money. Third, regulatory failure. Building regulations didn't adequately address cladding fire safety. Testing standards were insufficient. Enforcement was weak. Fourth, ignored warnings. Residents had formed a Grenfell action group that repeatedly warned about fire safety issues. Their blog post from 2016 predicted only a catastrophic event would force authorities to address the problems. They were tragically correct.
The consequences. 72 people died in the Grenfell Tower fire. Many more were injured. Survivors were traumatized. An entire community was destroyed. The fire exposed systemic failures in UK building regulations, fire safety enforcement, and social housing oversight. Similar dangerous cladding was found on hundreds of other buildings across the UK. A public inquiry is ongoing. Criminal investigations continue. Building codes have been overhauled. The UK government has spent billions removing dangerous cladding from buildings. But 72 people are dead because cost was prioritized over safety, and warnings from residents were ignored.